want to see it, but just so you know, only curse those things that you want people to know about. Okay. Today we had a little lecture prepared on using Pandas and doing data analysis with Pandas. Which is also what this slide says. So the idea of doing something specifically for data in many of our courses that we give to physical scientists, physics, astronomy, a lot of the data really comes as big arrays, n-dimensional arrays. That might be either, think of climate simulations. There's just a grid over the Earth and that's simulated. That could be astronomical data, so a telescope, basically also just a grid on the sky. Today, or what particularly this Pandas package in Python is very good at, is to deal with structures that aren't quite n-dimensional arrays. So we're going to see how we can deal with those within the context of Python. So we're going to look a little bit at data analysis, and even if it is just an n-dimensional array that you are working with, when you have data, there's always a few steps that are very common. You always have to read or write some data sets, and that means you have to deal with file formats. This is sometimes a bit more work than you want, because it's not the thing you're after, but it is a part of your workflow. And then usually your data doesn't come in as neatly as you want, unless you generated it yourself and you were careful. So if you wrote your own simulation and your output format is precisely the one that you need for your data analysis afterwards. That's not always the case, and so you might have to do some cleaning, selecting, normalizing, maybe get a subset or compute some derived data from that before you even get into finding out what your data has to say. You might be doing some modeling or computation of the data, so if you're doing simulations. And then probably at the end you would want to do some visualization or some other way of presenting the results. So today we're not going to do all of these because we only have an hour. So we're going to mostly look at the idea of reading, cleaning, and sort of analyzing the data, but not quite as much in how we read things, not so much as how we model things, and not so much about how we visualize. We'll do actually visualization and a few other lectures. Okay. So I want to go away from the idea of having just a rectangular array, and people often call this thing unstructured data. So the idea that there is big data out there, and we have so much data, and it's horrific because it's not structured and comes in all kinds of forms. You might have all kinds of different data, like patient data, or ships, meteorological records, Twitter data, documents on the internet. They could take all kinds of forms, right? So that is kind of unstructured. And even if it is somewhat structured, you might still have things that are less structured than you want. You might have to deal with missing data, or you might have data that you could put in an array, but each element means something else. It's not the same thing. It's not just the 0th, 1st, 2nd element. It's actually, temperature, pressure. Those are different variables that are more naturally described by a label and an index. So we're going to look at a few handy ways to organize data using these ideas of having maybe missing data, having some labels, things not being as structured as you might like. But I should say that I don't really believe that unstructured data exists. The only unstructured data is white noise. Anything else has a structure to it. It's just not as simple as an n-dimensional array. So you might need to look at the data, parse it. There might be text, so you might have to split it up in columns that are separated by something unusual. And you have to deal with missing data. There might be some points that aren't there. Those are things you have to deal with, but it doesn't mean it's not structured. And even if it's very, very unstructured, it just means that some of the stuff is just not valid. You just have to throw it out. So the first step is going to be this cleaning process where you take your data and you say, okay, this part is nonsense, this part is missing, but I either fill it out with something that means something, or I explicitly have an algorithm that deals with missing data, which would be better. And then you're going to give some labels to the different bits of information. Okay, so there's no, and so another phrase that you often hear in this data science era is that it's not just unstructured data, it's also big. There's a lot of data, and that's a problem for some reason. Now, the next question you should ask is, how big is big data? If I have a file that's 10 gigabytes, is that big data? Depends where you come from. So there's no sort of unique bigness scale. There's no big data. There's only data that is too complicated or too voluminous to deal with the tools that we have. So you could imagine that if it takes, let's say, 10 centuries to analyze the data coming from a particular telescope, then that is big data, because we can't really do that. There's no point in that. But even if our data is really small, like that 10 gigabyte file, but it's so unstructured or so complex to interpret that it takes a century to figure out what it means. Maybe it's encrypted, and we have to unencrypt it. So what is big is really a measure of how hard it is to handle. It's not something that is inherently a property of the data. So often when people say big data and get all scared, you'll find it's still quite organized. A lot of the big data that people talk about, the streams of data coming in, is extremely organized. I like the idea of telescopes data because, of course, it's very organized, but even Twitter feeds are extremely organized. They can only be 140 characters long, and it's all text. That's extremely structured. It is not unstructured at all. So it's fairly easy. And then the other often explosive parts are things that come in a table, like patient data or genomic data. Basically, you have a couple of aspects, and then you have some maybe a string. That's still very organized. So often you can think of not traditional array data still in sort of a tabular form. Basically, you think of it as an Excel file where you have columns and rows, and each column could have a label saying this column means that, and this row means that, or this is. And thinking of it in that way is the approach that Pandas takes. So not all data might come initially in that form, but a lot of data can be put in a sort of tabular form to help you manipulate it and make sense of it. So we're going to skip the idea of how you get from your raw unstructured data, whatever it might be, to your tabular format. We're going to see, okay, suppose we have it in a tabular format, what can we do with it? One of the things that is that you gain by using tables is that you could have mixtures of data types, so you don't have to have every element of your data be a floating point or even a number. You could have a string, you could have an integer, you could have Boolean, so true or false. You could store it in different formats too. A couple of common formats are the comma-separated values, JSON, Excel sheets, text tables, HTML for. So that's kind of what we're going to look at. Clear? So we want to look at tables. Although I would maintain that a lot of that unstructured big data out there is still just, you put it in a table. So here's an example of this unstructured random big data. Some random information. There's some name, there's an age, there's a height, an eye color, an employer. So this is not an array for a couple of reasons. Every element is of a different type. It's not a list because I have a bunch of labels there. So what do I do? How do I store this within Python? Like, how should I deal with it? It's kind of it's kind of like a record, right? It's like, this could be Freddy Krueger's patient's record. I can make two lists. I could have one list being the labels, so basically this column, and have one list with the entries. That could work. I do have to keep track of how those two are associated. I should be careful not to append something to this list and then there's nothing on the other side. So what I'd rather have is a data type that can take this together and store it as the sort of information that it is. Now Python has a data type for these sort of key value stores. It's not a way to say it. This is the key and this is the value. And they're called dictionaries. They are called dictionaries because basically you can look up a name and it gives you the result. So it's like looking up a word and getting its description. And they work exactly like that kind of way. And the syntax goes as I depicted here. There's curly braces to say I start a dictionary. There's the key and then a colon and the value. And you can have as many keys and values as you want. You can have any type used as a key. You can have any type used as a value. But you always have the pair. So you always have something, colon, something else. Key, value. You can't add just a key. You always have the key and a value. You can't add just a value. It's not a list because all the elements are different. It's not two lists either. It's got exactly the structure that you want for dealing with essentially a record. Okay. So I'm going to look at a few ways. By the way, who here has worked with Python dictionaries before? Right, so about half the audience. And so this is kind of what it works. It's since Python 2.6, 2.7, something like that. It's a built-in data type, which means you can use these curly braces, and it's a kind of natural notation. But there's other ways to construct it. The old way is to say dict and then assign 1 to 1 and 2 to 2, whereas one of the ones becomes a string internally. This is kind of funny. You could create one from, if you had a list of tuples already, where or a list of pairs of key values, you could take that list and convert it into a dictionary. And what's nice is that once you have this dictionary, you can do a lookup. Square braces do that lookup, so you do square brackets and then 2, and it'll look up 2, and it will find the value 2. Now, right now I've only got stored something that's labeled 1 and something that's labeled 2. To store an extra element, I can just perform a lookup that doesn't succeed and assign it to a value. So here, after I've assigned 3 with a label 3, then C contains 3 elements where 3 is right here. I think by default, when it prints the dictionary, Python prints it in alphabetical order according to the keys, which is why 3 is in the middle of 1 and 2. So there's no particular order here, because the keys will tell you what element is what. So that's dictionaries, and you can do a couple of other nice things. You can see what keys are in there, so then you just get a list of the keys. You can check if a key exists, so 1 is in C, but 4 is not in C. You can do things like set a value if there is no value yet, or if there is no value, make it a default. So here, if 4 doesn't exist, it takes the default 0. But if 1 already exists in the list, then you don't use the default, you use what was already there. So there's different ways of building these lists and accessing them by square brackets. So this is nice for just those key value stores. Now, what if we have a whole bunch of these? So what if for every key, I want to have several values? So that's one of the things that I don't have here. Every key has one value associated with it. Now, it's true, I could make lists of those, but what if that's what I have? What I have, one key and a bunch of data. So for instance, suppose that I want to associate with a set of names, the gender, and the number of times that the name was given to a newborn. So that's essentially a table. Could look like this. So here are 6 names: Anna, William, Emma, John, James, and Mary, their gender and their number. Now, each of these rows is essentially a record that I could assign to one of these dictionaries. By the way, these tables often have what's called an index or a key. In this case, I've chosen the key to be an integer, just ranging from 0 to 1. Because the names are unique, here I could have taken the name as an index too. It's nice when you're trying to build a data structure which is accessed by labels to have unique labels. And so the names might at some point not be unique. There might be an extra record that is also Anna, but it's a boy Anna. I don't know, fashion changes. And so having a unique key is often a good idea. That's why there's an extra key here. So here it's an integer, but it doesn't have to be. So tables like this are kind of the bread and butter of what are called relational databases. So if you ever want to look into those, you're dealing with these kinds of tables, but then a whole bunch of them that have somehow relations between them. That's not the topic of today. Today we're just going to look at this table. Now, there's no built-in type for tables like this, which is different from a language like R, which has so-called DataFrames that are sort of native to the language. In Python, it kind of stops at a single row, and that's this dictionary idea, right? So how would we store this? Well, there's in a way two possibilities if it isn't built in. We could either take the idea of having storing it by column. And so for each column, I would have to say, well, for key 0, the name is Anna. For key 1, the name is William, etc. And then for the second column, I would repeat that for key 0, the gender is F, key 1, it's N. So that's this idea. You could store a key val as separate dictionaries where every key is repeated. But you kind of see that that's a bit wasteful, because I'm repeating the same keys here on purpose. And you can see that it's wasteful. It's easy to make a mistake. I could mistype one of the keys, and things are just not very well. So you want something that is a little bit better. Now, you could go the opposite way. You could say, well, let's just store every of these columns as a NumPy array, or any old array, but NumPy array might work. And then just let the labeling take care of everything. So that would be more efficient in terms of storing, but I still have to make sure that I don't have some arrays that for some reason are longer than the next column. All the columns should be equally long. And you lose the idea of labeling that NumPy arrays don't have. So I can't ask for key 2 and get these. Well, if the keys are numbered like that, it's easy. But if the keys were not, it would be hard. Okay. And not only would I like to be able to label the columns, I'd also like to label the rows. So there's kind of room for an improvement here, and that's what Pandas gives. So Pandas is essentially using tables in Python using a DataFrame data type. I'm pretty sure that that the name DataFrame was borrowed directly from R, but that's fine. So Pandas gives you a new data type called a DataFrame that will store something like that. It has it's well thought out in trying to be practical. So it's not that hard to build a data type that does this per se, but the whole infrastructure comes with it with Pandas that you could read in an Excel sheet if you had one. You could read in a comma separated value, so it could write out into another format. So it has a lot of utilities that make your data immediately readable and useful. So many input and output formats. The API is fairly easy to use. We'll go through it a little bit. It's well tested, so you don't have to worry too much about it. It's aimed at high performance because it uses NumPy arrays under the hood, but it takes care of all of the nitty-gritty and making sure that it's a consistent table for you. So let's build a data frame. Here's that same set of data. I've put the name column in a list, the gender in a list, and the number in a list. I haven't done anything yet. And then I want to combine this data. So there's several ways to do it. Here's one way, using the zip function, which essentially combines these three columns into a set of tuples. So each of them is now its own record. I don't have any labels yet, right? I'm not using any of that yet. But I would like to import this with labels into a table. It's too much data to go into a dictionary, but it should fit in the table. So, by the way, these are the top 3 American girl and boy names from the year 1880, if you were wondering. So this data in this sort of list of tuples, I can put in a data frame. The data frames come from Pandas, so I import Pandas, and I give it a shorter name, PD, and then At some point I'll need some NumPy facilities too, so I'll import that too. And all I do really is I'm calling the DataFrame function with that data. And wanting to label the columns, I give the names of the columns as an option. So name, gender, and number. And once it's that, df will contain a data frame. So this is a table. It's called a data frame, but it is a table. Everything is labeled. You will see that it has labeled or put keys into the rows as well. Now here there are numbers, but they don't have to be. But since we didn't give any index to the rows here, the default is to make integers. So this is exactly the table we were just drawing on the slide before, but now it's in Pandas or in Python. Okay. So, by the way, if you've not noticed, I'm putting all of these commands in as if I typed them into IPython rather than Python. If you're worried about the difference, you can talk to me later, but this is essentially what you have. So we have index, numbers, headings, data frames. Okay, so to highlight this idea that this interacts nicely with file formats, I could take this data frame and use the toExcel function to write it into an Excel sheet. I might not want to store the index, and I do want to have the header. Those are options. And likewise, I could read Excel sheets. So somebody gives you an Excel sheet, you could say, well, read it in from Pandas Excel file. That reads in. Excel files can have different sheets, so you should specify which sheet you want, and then you can parse that and put it in the data frame. You can understand that if you've worked with Excel at all, the structure in there is a little bit more loosey-goosey than just a table. And so there might be Excel sheets that you don't, you read them in and they make no sense. If they're nice and tabular, if it's a table, it will make sense. If it's not a table, then reading it in as a table is just not sensible. Okay. And there's a number of tabular file formats out there that Pandas knows. It knows about JSON. It knows about HTML tables. It knows about comma-separated values, as well as the Excel sheets that I said. And it has readers and writers for those. So, for instance, now these are all text. Well, Excel is not really text-based, but it is text-based. If you're dealing with numeric data, you actually want to stay clear of all of these. You want to store this in binary. It's more efficient. It's faster to read and write. We're not going into binary data today because that's not really the point. But don't think that you have to use these, especially if you're using any sort of numeric data. Find a good binary format. NetDF, HDF5, something that's portable to go, or something domain-specific but accepted in the community. Please do that. But we're dealing with mostly text in this lecture, so we don't have to worry about it. Okay. Just as an example, if you wanted to write to a CSV, there's again a DataFrame.to CSV file name. Whether you want the index stored, whether you want a header, and then I can read it in again. I always like to do low memory is false for some reason. If I don't, some data sets seem to fail. Don't know why. So you can read and write to CSVs, and just to give you an idea of the difference between these formats, even within the inefficient text storage, there's a lot of difference. Here's a comma-separated value file. Here's the same thing in the so-called JSON format, and here's the same thing in HTML. So if you have the choice, obviously you're going to stick with this guy. You would think, except there's a standard on JSON, and there's no real standard for CSV. So people sometimes prefer JSON because there's sort of a prescribed standard, but it is a lot more verbose. It's essentially doing this repeated key stuff that I told you was very inefficient. That's how the format works. Here, I just have my table. So just so you know, if you want it, if you can and your CSVs are clean, it's a fairly concise way to store things. Okay, so that's the input-output. Now let's look at what we can do with the data frame, and then we can look at some data. So here's my data frame is still in DF. How do I access its rows and its columns, and how do I deal with that? And so the first thing I might want to know is, so the first thing I can do is I can say, okay, I want the column that is associated with the label name. And so columns are accessed with square braces, much like the dictionary. Remember the dictionary, but you get your whole column. It works for the whole column. So you get all of the names, and then once I have that column, so this just gives me a column, I can ask Pandas to describe the column for us. So it gives some statistics. In this case, it'll give you how many elements there are, how many are unique, what the top one is, which is kind of funny if it's text, but if it's numeric, it would tell you that. The frequency, and what kind of objects they are. And strings tend to be stored as objects, and so that's why it means this. This is funny, but the name of this column is name. So there's a label to this column. The label is used, instead of label, it uses name here, so that's why it says name. When I do the same with the number column, so do you have number described, it'll actually, because it's numerical, it will not just count, it will also give you mean, standard deviations, and some percentiles, and a maximum. And here you'll see that the name of the column was number, and the type is a 64-bit floating. I can do some more fancy things. I can ask for the gender column to count the values in it, and then it'll count that there are 3 values of F and 3 values of M. It will remember that the name is gender. So one of the nice things that I like about Pandas is that as you're doing this manipulation, and you're asking for a specific column, it keeps track of what that column was, what its name was. So it hasn't forgotten, when I just take the gender column, that the name of that was gender. So later, if I just assign this to some variable and I wasn't very careful choosing a name for that variable, I can still figure out what column this was. Right? I don't have to remember, oh, this was column 100, and 100 meant gender. No, it's kind of encoded. So that's a nice way to deal with data. It's a very sort of mature and responsible way to deal with data. Label your stuff. Also quite noticeable is that there's kind of 2 ways to get a column. Square brackets, but I sort of glanced over the fact that I can just do a period and a number. So all of these columns also become a member series of the data frame. So either one of the 2 will work. By the way, if you want to know all of the functions, you can do help data frame, and you'll get a whole bunch of functions. There's some other nice things. You can sort values. So you can sort them by number. So you just pick your column and you sort them by number. And then what's nice about that is that you could pick out the top one. So in this case, since it's just sorted from low to high, these are the smallest ones. So Emma and Anna. Again, I can count how many there are. I can get the shape of the whole data frame. So that's the number of records times the number of columns. I can sum up things, and I can get the data types of the different columns, etc., etc. Okay. So this is column-based, right? I can add a column, which is kind of like adding an element to a dictionary. So here's a I'm making a new data frame here. So here's a list. I make it into a data frame. Now the list is upside down. It's a column, and it has an index, and it has a name. The name of the column is 0. But then I can give that column a different name. In this case, REV, probably stands for revision. And now you see the column as a label of revision. So I can always change the indices of the columns if I want. If I forgot them, there they are. So that's all column-based. Now something funny is going to happen, and I don't like this much about Pandas. I have another square bracket accessor for this data frame, and go from 1 to 3. Now, square brackets before were columns. So we're selecting a column. In this case, they're not. They're selecting rows. Don't ask me why, but if you put in a range in square brackets, you get row 1 and row 2, and not row 3. As in all of Pandas, when you do slices like this, you specify the first element that you want and the first element that you don't want. So the first element I want is 1, the first element I don't want is 3. So it's a way to select records, parts of records. I can get more columns by doing this thing that I did with Dictionaries too. I just assign a value to a new column, and then all of the rows, each row will get a new value 5 in that column. So I just use a column, and it now suddenly exists. Same here, I can take the revision, add one, and make that a new column test. Here it is. You'll notice nicely that Pandas has a way of dealing with missing data. It's not as sophisticated as in some statistical packages, but it has it. What it does is it chose to use NumPy's NaN, so not a number representation, as an indicator that there's no data there. And it will figure out that if you add 1 to a NaN, if NaN means I don't know what this answer is, then you should still not know what the answer is. So NaN really means I do not know, and I do not know plus 1 equals I do not know, rather than 1. So it does that correctly. I can get the just a test column if I wanted to, and then I'll see everything has been promoted to float. Okay. Now, what if I do want to get rows rather than just selecting them with this funny extra square bracket? There's what's called an access function, access. You get access to the third row. Kind of funny. Here again, this row isn't just giving you the elements of the row. It'll still tell you, well, this first element was a revision. The second element was a new call. The third element, the test, will give you what name it was. The name of this third row was 3. I haven't labeled it explicitly. Its label becomes its number. Then I can append, say, one of these things. So I append the same column again, so the same row again. So access is the third row, and I'm appending it. Here it is. So I had it before, and I append it again. Now, you can only append things that are data frames, or sort of a subset of a data frame called a series, essentially a column. So you gotta sort of make it into a data frame first. But all these accessors, they all give you a data frame back. So you have a big data frame, you select something, it's still a data frame. Everything is labeled, it's still a table, it's just a subtable. You got to be a little bit careful with append sometimes. So this last part is a warning. If I just appended a list of numbers to my data frame, I would get them right here. All the other rows will now suddenly have NaNs, and I will have NaNs here. Because what happened is that when you append one data frame to another, it tries to match up the labels. And because this thing that I'm appending doesn't have any of the labels new call or rev or test, it just creates new labels for it called 0, 1, and 2. So new rows are created here. And if that's not what you want, you have to be specific and say, well, the stuff that I'm adding is supposed to be added to these columns. And then it will work as expected. Okay. So when you're adding data frames or appending them, make sure that the labels are there and that they line up. This seems tedious in this case, but there might be cases where in one data frame you have ordered your columns in one way, and in another data frame you have ordered them the opposite. This will automatically do the matching. Like the row that's labeled rev will only be added to for the column that is rev will only be added to other elements that also are rev. Okay, so that's kind of the quick overview of what you can do with Pandas. There is no better way than actually getting your hands dirty, because some of these are confusing and you have to get a little experience. And so I've picked two pieces of data, both of which are from open data initiatives. And this has now emerged in many cities in North America. New York City was one of the earliest one, although I think Chicago was even earlier. Cities put their data that is allowed to be public just out there. And so in this case, I had some data from New York City. There's some website that I forgot to put on here that looks at all the complaints, essentially, all the 311 calls. So 311 is a number in New York City that you can call if you have a complaint, something to. So it's not just an information number, it's like complaints. And so I think we have it on the website, or if not, it's in there? Good, okay. So it's there, it's zipped because it's a little big, but you unzip it, you get the CSV, and we could look into it. So suppose that the path to the file name is as listed there. I could read that CSV in and figure out how much is in here by asking for the shape of the data. There's about 100,000 records, and each record has 52 elements. If I wanted to know what those elements are, I'd ask for the column names. Data.columns will give me that. And there's things like the unique key. That should not be a surprise, it's a table. When it was created, when it was closed, what kind of complaint type it was, where it happened, if it was at a school, what the school name was, could have been at a ferry, at a bridge, lots of things in there. I could look at the elements of one of the rows, say I'm looking at row 0 just to get an idea of what's in here. Most of it is text. There's a noise complaint on the street. It's between 90 Avenue and 91 Avenue, apparently. The address is there, the timestamp. Some things are not available. A bunch of stuff. I could print the first 3 rows to get a bit of a better idea. And that gives me a subtable, right, from row 0 to row 2. And what Python will do to print that is, since there's not enough lines, there's not enough columns physically on the screen, it'll just take some of the columns, print those, and then take the next few columns and print those, etc., etc., etc. So it's a bit of a confusing way of doing this. If you're using the Jupyter notebook, when you're printing it, what it will do instead of this sort of folded structure is it'll just make something that's scrollable. That's kind of nice. So suppose I want to know, so I figured out, okay, there's a column called complaint type. What kind of stuff is in there? Now I could print them all, but it doesn't going to tell me anything because there's 100,000 lines to look through. But I could ask, well, from all those values, what are the unique ones? And I haven't put the input output here because it's still quite a few, but it's less than 100,000. So I can mix things from taking the values out of a column and passing it into this NumPy function that says unique, because the values are, because under the hood it's still a NumPy array. So it's kind of neat. We could take some of the columns. So this is now yet another level of selection. I can select just certain rows and just certain columns with this .loc, so location selector. And again, it gives me still a data type, a data frame. Okay, so everything is still labeled. You can get some complaint types. I can see illegal parking, when it was created, etc. So suppose we wanted to look at a complaint about noise. We could select just those, and this is a very neat construction. I ask which data, where the data column complaint type is equal to noise, straight, or sidewalk, and then I select only those into noise. So noise is a subset of the whole table where the complaint type is a certain type, and I could print it and I get a bunch of things. I get in total about 2,000 of those. So the way this works is that whenever you say column equals something, what it creates is a new column that is essentially just true and false values, depending on whether this is indeed the case, whether the data in that particular column is equal, or that particular row is equal to this. So some are true, some are false. And then whenever I feed this sort of a true-false array into data again, so I had this whole expression in here, and I feed it back to data again with square brackets. Now it says, okay, this is a Boolean array, so I'm just going to pick out the ones for which it's true. And so it's yet another way to do selections. So it's all about slicing the data and selecting the data. So now that I have this data of just street walk noise, I could ask, well, where do they complain most about street noise? So I could say, okay, well, here's my data noise, and here, let's see if it happens in Brooklyn. And it happens to be a column that says what borough they're from, or the noise was from. So I can see if it's Brooklyn. And then I can combine these two with AND. I can say, well, I want everything that it was a noise in Brooklyn, and that's my new data type. So you can do that by burrow as well. So you could say, well, let's just do all the noise. But now let's see in that noise how many times each burrow can be counted. So here's a nice application of this value count function where I say, okay, I take all the noise data and I take the column that's called burrow and I just count how many times there's a value here. And lo and behold, either it's more noisy in Manhattan or people are more easily annoyed by noise in Manhattan. But they're the top. Now, I could normalize things to say, well, maybe I should normalize by the number of counts in the burrow total. It could that too. Doesn't change much. Maybe I want to plot these things, and this is kind of nice. So it's a feature that it's crude, but there's visualization in Pandas. They say, I've got this data, let me just plot it as a bar chart. So you could get things like this. As I said, it's not particularly pretty out of the box, but it does give you a visual representation of Manhattan being the most noise complaint of the boroughs. And we don't have to do this with foreign data. We can do that with our local data. So since a few years, Toronto has an open data policy as well. And so a similar data set, if you want to play with it, is located here. And it contains, it's a subset because the real data set is a bit big, but it's about a third of the data of all parking tickets in Toronto. I forgot what year. Do you remember what year it was? 2015. So if you want more data, it's right here, opendata.toronto.ca. And if you want to know what this particular data is about, there's some information there. So if you wanted to get that data, I just wanted to show how that works. You need Pandas, because we're going to put things in the DataFrame. And then there's two extra packages that are useful to read this. Requests is something that can get a basically file on the internet and download it. And then IO is something that can take that read-in file and pretend it's a file. Why is that important? Because once I read in this URL with request.getURL, I want to pass it into readCSV, but readCSV was a function that reads a file. So IO essentially treats this bit of text that I get out, which is already stored in memory, treats it as if it is a file and passes it to readCSV. So that way, my function that reads a file doesn't really read a file, just reads this content from memory. So this is a way to get pretty much any accessible data on the internet into here, into a data frame with just 2 lines. So this is this has a number of columns in it. There's things like the date of infraction, fine account, location, a whole bunch more. But it's not as voluminous as the New York data. But basically all parking tickets in 2015 in Toronto are in here. It has, for instance, a field for the province, so you could figure out where it is. So here are some of the things we could ask ourselves, given that we have this data. What's the most common fine? Like if I get a parking ticket in Toronto, what am I most likely to be paying? I can ask what province got the most parking tickets in Toronto. I would guess it's Ontario, because Toronto is Ontario, but other provinces, who visits Toronto most? I can figure out how many tickets were given for parking close to a fire hydrant. Somewhere there's one of these location fields might have the word fire hydrant in it, and I'm going, okay, that's interesting. I might want to know what streets get the most parking tickets, and figure out where I shouldn't even try to park. And I personally would like to know how long those streets are, because that gives you more of a chance of knowing what's the probability I get a parking ticket, but that's not in this data. So I'm not going to give you answers. This is either homework, or you can sit here and try it if you want. But in principle, all the techniques you need are there. So basically we're selecting things. So most common fine per ticket. Well, one of these is the fine. I forgot which one, but one of them is the amount, set fine amount. So, selecting those, that column, you should be able to figure out what is the most common amount, right? Provinces in there, so you can select or you can count by provinces. We've seen how to do it for boroughs, same as for provinces. We could try and figure out in the description, I think is probably where you'll find fire hydrant. You'll have to look at the data first. This is something that is almost always the case with text-based. Turns out all of these descriptions are all in capitals. So if you start looking for it in lowercase, you're not going to find them. It's something you kind of have to know, right? I've tried all of these except the street in Toronto got the most parking tickets. Given that Yonge Street is the longest street in the world, you would think that it's Yonge Street, but I don't know. Maybe people are a lot more careful there. Yeah. Questions? Ideas of what else we could ask for this particular data? If you want to stick around and open your laptop and try it out, you're welcome. We can do that. We can try and answer some of these questions. There is, well, a few things. First, if it's not really text-based, this is probably not the way to go. If it's a mix, maybe still. So like you want to know what your maximum signal is that comes out of your telescope, this is not the way to do it. Just take your array, you count, and you'll be faster. There is a limit to what this can do because it does read the whole thing in memory. So if your data is too big to fit in memory, this is not your tool. As far as I know, there's not really a distributed Pandas yet. And so then this is not where you would go. The other thing that doesn't really help you here is that there's no parallelism in here. So if you ask for instance this question, okay, I want everything that is either noise and in a certain borough, you think that those are two things that I can query at the same time. I could have two processors, one asking, hey, what are the noise records? And one is, what are the Brooklyn records? That's not happening here either. So you're not taking advantage of that either. So anything that you want to do at scale where you have to divide out the work, you still have to do that by hand. Now you could, of course, you could take the CSV and outside of Pandas chop it off in pieces. So I've given here the text. There's nothing that prevents me from saying, okay, let me find the different lines in the text and then split that up and give each of them in a different data frame and then process that in parallel. It's a possibility, but it's not in Pandas itself. So that's obviously something you'd have to do yourself. So those are the main limitations. But it's in Python. So everything that you do as a sort of a built-in selector will be fine, but then around that you're probably going to do some scripting at some point. So you want to try and get away from that. Anytime you use Pandas and data analysis and you find yourself writing a loop, you might have done something wrong. Because the loop should be in one of these interfaces already. So this is thinking of it in terms of data frames or in terms of vectors. Now there's going to be cases where you can get around that, I'm sure, but you should be wary of that, and that becomes worse in Python because Python is kind of slow with loops. So.
I find unless I'm doing it.
Yes. The syntax is slightly confusing because if I don't look at it for a few months, I have to remember, okay, which one gives me a column, which one gives me a row, what happens with an append. Because when you append to a data frame, it doesn't actually append, it just creates a new one that is the sum of the old ones, which is fine. That's one way to do it. But so there's a lot of little things to remember. So you're right. If you're not working with it all the time, there's stuff you have to look up. On the other hand, once you've written it and it's sort of there, it's not too hard to understand what it meant. after the fact. So it's a little bit, it documents itself more or less. Not really, but more or less. But yeah, you're right. There's and the ambiguity in the square brackets being a row in one case, and I find that unfortunate.